All right. I do not know why my lips look so blimmin' red. They're inflamed from the cold season, something like that. Anyway, all right. So here we are. Graphing functions. So doubtless this is going to ask me to graph functions. So for this purpose, I will get up GeoGebra and I will cut out a little bit of the XY plane from -5 to 5. That seems somewhat suitable just as a default. And yes, we'll proceed with trying to answer these questions. Okay, for problems 1 to 5, construct a table of at least 4 ordered pairs of points on the graph of the function and use the ordered pairs from the table to sketch the graph of the function. So how to do that for problem 1, 2, and 3. For problem 1, we can see that this is a quadratic. It's going to have the shape of a parabola, like a U shape, opening upwards. It's going to be symmetrical down the middle, and it will be translated 2 units downwards from the origin. And therefore, the appropriate ordered pairs to put in my constructed table will be symmetrical about the origin. Notice that it says of at least 4 ordered pairs. So it's fine if I do, for example, 5. So I'll do -2, -1, 0, 1, and 2. To obtain the outputs, just follow the rule of the function. So square the inputs and subtract 2. And from this we obtain 2, -1, -2, -1, and 2. Symmetrical. And now to graph it. When graphing, consider using a different color like red, something which can sort of stand out against the black with which you made the XY plane in the first place. So here and here and here, these points will all be on the graph. And the most important thing at this stage is to not connect the points up with a ruler or straight edge, because that means that you don't understand that it's a continuous curve, a continuous curved function, and it sort of smoothly connects the points. So it's tempting to sort of like, just go ahead and connect up all the points. But instead, for accuracy's sake, you should make sure that you know what happens when you put in 3 into the function. Now, extending your table a little bit and putting it out of order, that's totally fine. 3 squared minus 2 is 7. And here will be 7 as well. So these dots will be off the screen. But the most important thing is to make sure that you don't let the curve come out there, because that would mean that it's moved past 3, which is false, wrong. So here we go. best as you can, try to connect the points, although it's difficult on a computer using a graphics tablet to do this. But it'll look something like that. Next up, we have the function root of x plus 1. So in this case, we need to think about appropriate inputs because we can't take the square root of a negative number and graph it on the xy plane. So what would give me a negative number? Any value of x that is strictly less than negative 1. So in your table of pairs, input negative 1, 0, 1, 2, and 3. This will output 0. This will output 1. And for all the rest, it'll be, let's see, root 2, root 3, and then root 4, which we can actually evaluate to be 2. There I go. The effect of this is that it's these classic sort of square root graph, which is half of a parabola, but opening up towards the right. And because there's a plus 1 there, that has the effect of translating the graph to the left by 1 unit. So it'll be here and here. And at 3, it'll pass through this sort of integer point or lattice point there, nice and cleanly. But for the intermediary values, you're not really too sure, not 100% sure. Root 2, that I do actually genuinely recommend, like sort of kind of learning. It's about 1.414. Root 3 is about 1.732. It will be a kind of smooth function like that, something like that, opening up towards the right. In problem 3, we understand that this is a constant function. It only and exclusively outputs the number 9. So in my xy table, I can include these 5 values, but it will just simply be 9 in all the y coordinate entries. And we can see that this sort of portion of the xy plane is not sufficient because all the points are off the screen. So I'll zoom out in GeoGebra, or rather zoom in on a different portion. This will be a horizontal line passing through x passing through y equals 9. This should be all right, but we need to expand it, I guess. There. And there. But notice that it says use the ordered pairs from the table to sketch the graph of the function. So strictly speaking, I would be obliged to indicate that I recognize that instruction. So I should do explicit points there and there and there, and there, and there. And now for the fourth function. We're not too sure what this will look like. Start a new page. This is a piecewise function. A piecewise function. It is a function that is defined in two pieces. Execute this piece if the input value x is strictly less than 2, and execute this piece of the function if the input value x is greater than or equal to 2. So we need to pause and think about what these pieces actually do. This here is a linear function with a downward slope of -2. It will pass through 10 on the y-axis, but it will never actually meet the y-axis. In fact, the sort of greatest value will be anything that's strictly less than 2. So, but if I were to input 2 in there just to see, that would be 10 minus 4, so that would be 6. That would be 6. So I see. Kind of interesting. All right. Anyway, and this is a parabola, which is translated 2 units above the origin. Now, as for ordered pairs, which would be useful to have in the graph and to know for a fact, it should include 3 points that are above 2 and 3 points that are below 2. So I'll do 0, 1, and 2 for the 3 points below, and 3, 4, and 5 for the 3 points above. That sounds pretty good. And okay, just simply work out what the y values are. All right. If x is greater than or equal to 2, square the input and add 2. Okay, so over here, it would be 9 plus 2, which is 11. It would be 16 plus 2, which is 18. It would be 25 plus 2, which is 27. And if the input is, oh, hold on just a minute. Okay, 2 itself is included, of course. So square 2 and add 2. All right, so I get 6. But here, for 1, because that's strictly less, 10 minus 2 times 1, well, that would be 8. And 10 minus 2 times 0, well, that would be 10. So these are for the first piece of the function, and these are for the second piece of the function. Now, we are to sort of plot this, or graph this rather. So how are we going to do it? I mean, these values seem very large. So I think everything is above, all y coordinates are greater than 0. Also we see. So perhaps something perhaps I could do something, and everything is in the first quadrant. So perhaps I could do something like this. Zoom in just a little bit. All right, so it's going to be a difficult one. Now, best practice here would actually be compressing, sorry. No, that's right. Compressing the values on the y-axis, something like that. But nonetheless, we proceed. So for this part of the function, at 0, we read 10. And at 1, we read 8. And at 2, well, 2 is not actually included, but we would obtain 6. So what do? We do a kind of hole like that. It's an acknowledgement that the function does not actually pass through that point there. And now for the second part of the function, and I'm going to do it in blue. So 2 would be at, oh, I see, 6. Interesting. All right. 3 would be at 11. So best as I can, something like that. 4 would be at 18. And 5 would be at 27. So something like there-ish. And, you know, you're not so like, where would it actually start? Well, it would actually start like down there, the quadratic would, and it would pass through all those points up there. I want to see if I can actually do something. If I can just sort of do that. Okay, that's brilliant. Okay, that's best attempt at this piecewise function. Next up, we have another piecewise function, and it has 3 pieces. One for when x is strictly less than -2, one for when x is between -2 and 1, and one for when x is greater than or equal to 1. So how to get appropriate values? Make your table. What would I recommend? The thing is, like, for this central piece, you know that it's just a constant function. It's always just outputting 2. And so it's just going to be horizontal and output 2. And you know that this one is an upside down parabola. So it'll be like that. And then this one is a linear function. So it'll be like that. And these are like glued together somehow, but we don't know if they're glued end to end. So what we're going to do is we're going to pick up the number 1. We put it in there and we get 6. But we put 1 in there and we get 2. And so it will have a jump right there. At 1. Whereas if we input -2 in here, we get 1 minus the square of -2. So 1 minus 4, which is -3. -3. So it goes from 2 down to -3. So it will be like that. But then we think about the sort of shape of the parabola, and we recognize that if it just said negative x squared, it would be opening up downwards, and its maximum would be at the origin. But because it has a +1 there, it's that same parabola but translated upwards by 1 unit. But we're only considering that portion, that leftmost portion of it, where the input value has to be strictly less than -2. So it'll be down there like that. Okay, so we have in our minds now a kind of fuzzy picture for how it will look, or how it should look. So now we need to think about what are appropriate input values. We would want 2 for this piece, 1 for this piece, and 2 for this piece. So I'll say -4, -3. That covers the bottom piece. 0, that will cover the middle piece. And 1 and 2 will cover the top piece. When I input -4 into there, I get 1 minus the square of -4, which is 1 minus 16, which is -15. When I input -3, I get 1 minus the square of -3, which is 1 minus 9, which is -8. And for here, I know that I get 2. And for here, I just simply have to add 5 onto the input. So that will be 6, and that will be 7. And so here are the layers. That's the bottom piece, the parabolic piece. This is the middle piece of the function, the constant function. And this is the top piece of the function, the linear piece. Linear piece, constant piece, parabolic piece. Now we consider the outputs. They range from -15 all the way up to 7. So now we go to GeoGebra and try to cut out an appropriate portion. Okay. All right. Okay, so I'm going to use this portion, this one here. And then I'm going to graph it. And I'm going to use the colors that I chose. Okay, so for For 2, it will be 7. So it will be there. Oh, right, the appropriate colors. For 2, it will be 7, so the output will be there. For 1, it will be 6. So there's that output. For 0, the answer is 2. For -3, the output is -8. And for -4, the output is -15. And then we think about where to, right, so for the middle piece, it does not include 1 in the input range. And therefore, I will put a hollow dot there. But it does include -2, and therefore, I will also plot that one. And because it's a constant function, I can connect up the points like that. The top piece of the function is linear, and so I can connect those up like that. And then the bottom piece of the function is parabolic. And indeed, if we were to input -2 into here, it would be 1 minus the square of -2, which is 1 minus 4, which is -3. But that's not a legitimate input. So that'll do. So there it is, the 3-piece function. And now we should check all of these. Everything should be checked. Okay, we are in agreement. They did it symmetrically as well. That's nice. And here, we are also in agreement. They appear to have gone through points that actually output whole numbers, which I like. And notice that they had axes that don't necessarily have equal markings. But nonetheless, we agree. This is a constant function, just as I stated. And there you go. This is a piecewise function, as stated. And notice that we'll want to plug the quote-unquote cutoff point, x equals 2, into the top equation, as stated. And here they essentially agree with me, but as you can see, they've compressed their y-axis to fit in this information. All right, and last of all is the 3-piece piecewise function. And they put in the appropriate cutoff points, and they have the hollow dots to acknowledge the discontinuity or jump discontinuity, which is good. So that means it is all valid. So we'll save this work now. This is graphing functions. We'll save it to our desktop. Great. And we'll proceed to combining functions. The problems in combining functions. We combine functions to create a composite function. Or I've heard some people say composite, but anyhow. Oh, no, beg your pardon. In the arithmetic of functions, you can add them, subtract them, multiply them, divide them, or compose them. Collectively, I refer to all those operations as combining functions. So I really meant to say that if you compose functions, you create a composite function. Now, for problem 1, we are provided with a pair of linear functions. F is the linear function 6x plus 2, and g is the linear function 10 minus 6x minus 7x. And we are to compute f minus g of 2. So how do we do this? How do we do this? F minus g of 2 is f of 2 minus g of 2. F of 2 minus g of 2. And f of 2 is 14. And g of 2 is negative 4. But hold on just a minute now. Be careful, because we are to subtract negative 4. In fact, the output will be 18. And now we are to compute g minus f of 2. G minus f of 2. So that would be g of 2 minus f of 2. G of 2, as computed above, is negative 14. F of 2, as computed above, is 14. So negative 14 minus 14, which is negative 28. And now for part C, we are to compute FG. FG. When they're written next to each other like this, I've seen in some books that this is asking for the composite of f and g, but I think in this context it means f times g, but we'll soon see. So what you do in that case is you quite literally just multiply the definitions of the functions together. So this would be 6x plus 2 multiplied by 10 minus 7x. And for this, we employ the rule FOIL, first outside, inside, last, or simply just expansion, straightforward expansion. So that would be negative 42x plus 60x minus 14x, which is 46x. Oh, that should be negative 42x squared. So plus 46x, and then plus 20. And then f over g of x. So this is the quotient of the two functions, the quotient of f with g. So that would be 6x plus 2 over 10 minus 7x. But we'll have to check these to make sure that they are correct. So 18 is correct. Oh no. Oh, right. Uh-oh. I made a mistake. G of 2 was -4. Shame. All right. That's right. It's even right there. So -4 minus 14, which is minus 18. Okay. All right. This is simply looking at that product. And then here, this is this is the quotient of the two functions. So that's all. In problem 2, we have a pair of functions, p of t and a of t. One reason why I really admire these notes is because they don't just do everything in terms of f and g. You know, a bit of notational variety, which is fantastic. Gets you all set up for everything. So first, we are to compute their sum. And for that, you simply add them together. So 4t squared take t squared is 3t squared. Then 3t just by itself. And then -1 plus 2 is plus 1. And for part B, we're to do function A minus function P. So 2 minus t squared, that's the definition of function A, minus 4t squared plus 3t take 1. That's the definition of function P. Notice how I bracket them. And when we do this and perform this operation, we get -5t squared for our quadratic term, minus 3t for our linear term. The minus 1 will turn into a +1, and then 1 plus 2 is 3. For part C, PAT. That's the product of the functions. If it were the composite of the functions, then there would be sort of like nested brackets. It would be P of A of T, like that. But instead, this is just the product of the functions. So for that, we just write the definitions of the functions next to one another in brackets and expand and simplify if we can. That's officially what to do for function multiplication. And in this case, of course, we can actually expand and simplify things. So it'll be -4t to the 4. Now, to not risk making mistakes, it's better to just expand and multiply everything by -t squared first. And then multiply everything by 2 next. And then collect like terms. So we get -4t to the 4 minus 3t cubed plus 7t squared plus 6t minus 2. Just like that. For part D, we go to compute P over A of -2. So to do so, it is not asking us to do p of -2 divided by a of -2. Instead, it's asking for the quotient of the functions first, and then to input -2 into those. But as you see in this particular case, it's the same. So that's on top. That's on the bottom. And then we compute -2 all square. I mean, I'll just compute the top. So I get 21. And down here, I get -2. So -21/2. And now we must check. We must check everything. All right, so we'll check everything. That's correct for the first one. That's correct for the second one. No, that's false. So where's the error? Okay. Let's see. Oh, I see. -1 times -t². That should be a plus right there. And because that's plus t² plus 8t², that should be a plus 9t². And now it's fixed. Okay, and last. No, this is also in error. Okay, so I need to fix this. We'll try again. Try again completely. Just put -2 into P. And put -2 into A. Okay, that should be 4. 4 times 4 is 16. And 16 minus 6 is 10. And 10 minus 1 is 9. And this is 2 minus 4, so -2. Did that fix it? Yes, it did. Okay, that's good. Okay, now for problem 3. Now for problem 3. Okay, we're given two linear functions, h and f. H of z is 7z plus 6. F of z is 4 minus z. And our first job is to compute the product of the pair of functions. Okay, so just put the definitions of the functions next to one another in the order given and multiply them out if it's possible. So this will be -7z² plus 28z minus 6z, so plus 22z plus 24. Next up is f composed with h of z. So what we do is we pick up the definition of h and we put it into f in the spots where the input goes, and we put it in brackets. So f circ h of z will look like this. So I'm going to do, here's what f usually looks like, but where I see the input z, I replace it with h, and I do it in blue. So just like that. And then I compute it. Negative 7z, 4 minus 6 is minus 2, just like that. H circ f, or h of f. That's another way to say it. This time you pick up f and you put it in h. So 7, open brackets, 4 minus z, close brackets, plus 6, and compute. So we get negative 7z plus 28 plus 6, which is plus 34. And finally, h of z. So we pick up h and we put it into itself. Seven, open brackets, 7z plus 6, close brackets, plus 6. Compute 49z plus 42 plus 6, so plus 48. And check. Everything must be checked. Everything must be checked. So here we go. Okay, the first one is correct. And the second is correct. And the third is. And the fourth is, and that's good. All right, problem 4. We're given two functions f and g. F is a quadratic function, f of x equals 6x squared. And g is a quadratic function, g of x equals x squared at 3x, take 1. First, compute their product, g times f. So pick up the definition of g in brackets and put it first. Then pick up the definition of f in brackets and put it second. And carry out the multiplication. So this would be 6x to the 4 plus 18x cubed minus 6x squared. Part B. F composed with g, or f of g of x, f of g of x. Pick up the definition of g and put it inside the function f in brackets. So 6, open brackets, and here where x would be, is going to go the definition of g. So x squared at 3x take 1. But we have to carry out the computation. We have to square this quadratic and multiply it by 6. All right, so let's see. So what you can do is you can do like a 3x3 table with this along the top and this down the side. But try doing it in your head. Try doing it in your head. These will combine together, and then these will, and then these will, and these, and these, like that. It's a nice pattern to get used to. All right, so let's do it. So x to the 4 plus 6x cubed plus, okay, 7x squared, I believe, plus, oh no, it'll be minus 6x, and then plus 1. All right, and then expand and multiply everything by 6. Huzzah. For part C, we have to compose them the other way around. Function composition, unlike addition and multiplication, is not commutative. You cannot swap around the functions as you like. It's like putting on socks and shoes. If you put on your socks and then your shoes, this is very different to putting on your shoes and then your socks. Okay, here we go. Pick up the definition of f and put it into g. So 6x squared will go there, and then square, plus 3 times 6x squared, and then take 1. And then compute. You must square the 6 and the x squared. So we get 36 x to the 4 plus 18 x squared. Take 1. Finally, compute f of x. So put the definition of f into itself. So 6, open brackets, 6x squared, close brackets, squared. And we compute. And now we check. Everything must be checked. Okay, the first one is correct. And the second is correct. And the third. And the fourth, and that's good. And now the fifth problem. Okay, so we have two functions, r of t and a of t. Notice t is restricted to be greater than or equal to 0. We have to make those considerations when we compose these two functions together. All right, so let's just begin. So part A, R of A of t. Pick up the definition of A and put it into R. Like that, like that. And then compute and think. We have the square root of a square. Oh, so I guess they undo each other. So I just have t plus 2 minus 2. So what, that just turns into just t? Well, it would seem so, right? But if you were not allowed to have a negative value of t before, what makes you think that you can have a negative value of t now? It should be restricted as well. All right, okay. When a function just outputs the input, that's called the identity function. So this is the identity function, but with a restricted domain. Okay, now A of R of t. You pick up the definition of R and you put it into A. So open brackets. And where you see t, put root t minus 2. And then the plus 2. Root t minus 2 plus 2 is root t. And when you square that out, you get t. But I believe that t has to be greater than or equal to 0 as well. But who knows? Maybe he'll disagree with me. I don't know. Let's see. Okay, so they do not make similar comments. Well, I was always taught that restrictions of domains, like domains don't become expanded unless you insist upon it. But anyway, they're correct. So save now to my desktop. And begin something new. So I'm going to look at inverse functions now. Inverse functions are like reverse functions. You can zip up your clothing, or you can unzip. Inverse function. The inverse of adding to is subtracting to. Okay. So, question 1. We are given this function called h, which is a linear function, 5 minus 9x. And we are to find the inverse of this function. So in this case, we can just think it through. What happens to my input? Well, first I multiply it by -9, and then I add 5 to it. Multiply by -9, then add 5 to it. So what is that story? Reversed. First, subtract 5, then divide by -9, right? That's the reverse of that step, of those steps. So what would that look like? It would look like x minus 5 divided by -9. Like that. But that doesn't look very pleasant, so I guess x minus 5 over -9. Better, but you don't want to have a negative sign on the denominator. A lot of people don't like the look of it. Okay, so I guess I'll make the numerator negative then. Simple. Just swap them around. There. That's inverse h of x. Inverse h of x. Do not say h to the minus 1. That is wrong. It's wrong to say that. So you can see that that is right. That is right. But what have they done in step 5? They've composed h with its inverse. When you compose a function with its inverse, you get the identity function. You get the function which does nothing. It's like if I have a machine which adds 2 and a machine which takes away 2, and I stick them together, I get a machine which does nothing. It just gives the same output as the input. Okay, for problem 2. We can do similar thinking again, if we want. So let's try it. First, I've multiplied my input by 1/2. Next, I have added 7. So what is the exact opposite and reverse of those steps? First, subtract 7. And second, divide by 1/2. So what does that look like? So I write inverse g of x. First, I have to subtract 7. Okay. So I write x minus 7 and put it in brackets. And then I have to divide by 1/2. Okay, just like that. But people don't like the look of this. It doesn't look very pleasant. Dividing by 1/2, that's just like that. And then expand. So 2x minus 14. And we check. We always check. And that's correct. For problem 3, now I will do a different technique. Because this technique takes a little bit too long. And it doesn't quite work when it comes to problem 6. It doesn't fully work for problem 6. So what is this new technique? First, just write the function like this. Y on the left and the function definition on the right. Then try to get x by itself on one side. X by itself on one side of the equal sign and no mention of x at all on the other side of the equal sign. This is called isolating x. So y minus 1, that's my first move. Just subtract 1 from both sides. Here's my next move. Take the cube root of both sides. That will get rid of this right here, which cubes x minus 2. And finally, add 2 to both sides. So 2 plus cube root of y minus 1. And the last step is to swap around the variables y and x. Now we see that inverse f of x is 2 plus the cube root of, what do I put here? Not y, I put x. And there you go. And we will see if that is correct. Okay, so instead of writing the cube root, what they wrote is to the 1/3, but it's equivalent, so it's okay. Okay. Problem 4. Okay, so just write y equals the 5th root of 2x plus 11 and try to get x by itself. Raise both sides to the power of 5, then subtract 11 from both sides, then divide both sides by 2. Both sides by 2. And now express your inverse function. So would I write y to the 5 minus 11 over 2? No. Write x to the 5 minus 11 over 2. And there you go. And that's correct, and that's good. For the 5th problem, we see that x is on the numerator and denominator. It seems to be mentioned in 2 places, and it seems not possible to untangle it, but we will see. How can I get x by itself? First, multiply both sides by 5 minus x. This is sometimes called cross-multiplying, sort of, like this. Now expand on the left, like that. But why would I do that? Because now it seems almost impossible to get x by itself. Move this negative xy over to the other side. Just like that. And the goal here is to factor out x like this. And then we can get x by itself by dividing by 4 plus y. I just swapped around the sides as well because it's what I'm used to. So that's it. That's how you get inverse f of x. So now just replace y with x. Just like that. And we will see. And we see that it's good. All right, last of all, we have the sixth problem here. So we begin again. Y equals 1 plus 2x all over 7 plus x. Multiply. Expand. Bring everything mentioning x to one side and everything else to the other side. Factor out x. And divide through. And now, here is your inverse function. Just like that. And we check. Everything must be checked. And that's correct, and that's good. Okay, now we must save this. So this is inverse functions. And who is next? Chapter 3. That finishes chapter 3. Oh, I see. Common graphs and then polynomials. Right. Oh, beg your pardon. Okay, so no problems exactly for those. And parabolas. Okay, so this looks cool. So we have to find the vertex, y-intercept, and x-intercepts. So time to drink water. Be well, be well.